Lecture 3. Electronic effects and reactivity of organic compounds. In this video lecture, we are going to discuss electronic effects and reactivity of organic compounds. Part 1. As we know from the video lecture 2, chemical bonds can be non-polar covalent, polar covalent, and ionic. The nature of the sharing of the electrons in the chemical bond is determined by the electronegativity values. Electronegativity is a measure of the ability of an atom to attract electrons. Electronegativity values for elements commonly encountered in organic chemistry are presented on the slide. Carbon-carbon and carbon-hydrogen bonds are examples of non-polar covalent bonds. A bond between carbon and oxygen is an example of a polar covalent bond. An oxygen atom is more electronegative than carbon, and therefore it will more strongly attract the electrons of the bond. In chloroethane, two carbon atoms are not equivalent. The carbon-chlorine bond is polarized due to the higher electronegativity of the chlorine atom. The polarized carbon-chlorine bond of chloroethane polarizes the carbon-carbon bond through the inductive effect. The inductive effect is the polarization of a bond by the atoms or groups of atoms attached to it. Induction causes the formation of partial positive and partial negative charges. The inductive effect operates on sigma-bonded electrons. Graphically, the inductive effect is depicted with an arrow. The inductive effect is transmitted through the carbon chain, but it weakens away along the chain. Substituent attracting the electronic density of a sigma bond stronger than the hydrogen atom exhibits a negative inductive effect -I. Such substituents generally reduce the density of the electronic system, and they are called electron-withdrawing substituents. When substituent displaces the electronic density of a sigma bond to the carbon atom, it exhibits a positive inductive effect +I. Such substituents increasing the electronic density in the chain are called electron-donating substituents. They include alkyls, metals, and anions. Application of inductive effect. The phenomenon of inductive effect is very important in organic chemistry. Let's consider how it applies to the reactivity of alkyl halides. Alkyl halides are more reactive than corresponding alkanes. The reason is the presence of carbon-halogen bond and inductive effect of the halogen substituent. Strength of carboxylic acids can be also explained using the conception of the inductive effect. An acid has a tendency to give a proton. The strength of an acid depends on the ease with which an acid loses protons. Thus, a strongly electronegative group that helps in removing the proton from the hydroxyl group of the acid will have the effect of making the corresponding carboxylic acid to be a stronger one. Resonance. A single Lewis structure cannot satisfactorily represent some covalent molecules or ions. The carbonate ion is an example. The structure on this slide is not an accurate representation of the ion according to the experimental evidences. Evidences demonstrate that carbon-oxygen bonds are equal. Oxygen-carbon-oxygen angle is 120 degrees, and each of the oxygen bears the same amount of negative charge. The structure should represent equal distribution of electrons among the three oxygen atoms. Lewis structure failed to do this. Chemists developed the resonance model. In order to represent a molecule or ion with resonance, it is necessary to draw all possible structures that differ only in the location of the pairs of electrons. For the carbonate ion, we can draw three resonance structures. None of these structures really exist. There is only one actual structure that is called a resonance hybrid of three Lewis structures, which are called resonance contributors. The properties of the actual molecule are the weighted averages of the properties of the resonance contributors. Three resonance contributors of the carbonate ion have equal energy and contribute equally to the structure of the ion. In some cases, resonance contributors for molecules are not all equivalent. For example, nitroethene has two equivalent and one different resonance contributors. In the third resonance structure, the carbon is positively charged and both oxygens are negatively charged. The third contributor has a separation of charge. It is a minor contributor to the resonance hybrid of nitroethene. The more resonance forms one can write for a given system, the more stable it is. That is, the greater its resonance energy. This slide summarizes information about resonance, resonance hybrid, and contributing structures. There are examples of drawing resonance contributors and resonance hybrid. Mesomeric or resonance effect. Before defining mesomeric effect, we should define what delocalization is. Delocalization is the phenomenon in which bonding electrons of some molecules bind several atoms instead of two. Delocalized bond is a covalent bond, molecular orbital of which covers more than two atoms. Delocalized bonds are almost always pi bonds. They are characteristic of conjugated systems. The presence of alternating pi and sigma bonds in a molecule, such as benzene, is known as a conjugated system or conjugated pi bonds. Conjugated systems can extend across the entire molecule, as in benzene, or they can comprise only part of a molecule. A conjugated system always starts and ends with a pi bond, or sometimes with a charge. The electron withdrawing or releasing effect, attributed to a substituent through delocalization of p or pi electrons, which can be visualized by drawing various resonance structures, is known as mesomeric effect or resonance effect. It is symbolized by M or R. Negative resonance or mesomeric effect. It is shown by substituents or groups that withdraw electrons by delocalization mechanism from the rest of the molecule and are denoted by -M or -R. The electron density on the rest of the molecular entity is decreased due to this effect. Positive resonance or mesomeric effect. The groups show positive mesomeric effect when they release electrons to the rest of the molecule by delocalization. These groups are denoted by +M or +R. The electron density on the rest of the molecular entity is increased due to this effect. Some examples of mesomeric effect are shown on the slide. In most of the cases, resonance effect is stronger and outweighs inductive effect. And finally, some chemical consequences of electron delocalization. The acidity of phenols is due to its ability to lose hydrogen ion to form phenoxide ions. Phenoxide ion has greater stability than phenols, as in case of phenol charge separation takes place during resonance. The resonance structures of phenoxide ions explain the delocalization of negative charge.